You know what's funny about control systems? You're surrounded by them right now. Literally, right now, as you're lying there, your body is running dozens of them without you thinking about it. Your body temperature is holding steady at something close to 98.6 degrees Fahrenheit, and it's not because you decided to keep it there. There's a system handling that. Your breathing is adjusting itself, slowing down as you relax, and you didn't send a memo to your lungs about it. Something is measuring, comparing, adjusting, over and over, every second. And that's really what a control system is. At its heart, it's just a way of keeping something where you want it, or getting something to where you want it, by constantly checking and correcting. That's it. That's the whole idea. Everything else, all the math, all the diagrams, all the jargon that makes control theory seem intimidating, it all grows out of that one beautifully simple concept. But here's the thing. Simple concepts have a way of getting complicated fast when you try to make them work in the real world. And the story of how humans figured out control systems, how we went from crude mechanical tricks to the sophisticated theory that governs everything from your car's cruise control to the autopilot on a transatlantic flight. That story is one of the most fascinating threads in all of engineering. It stretches back thousands of years, and it's full of people who are trying to solve very specific, very practical problems, and who stumbled into ideas so deep that mathematicians are still chewing on them. So let's start at the very beginning. And I mean the very beginning. The oldest control device we know about with any real certainty is something called a float valve. The concept is ancient. We're talking about water clocks in places like Egypt and Babylon, maybe 300 years before the Common Era, possibly earlier. Here's what the problem was. If you want a water clock to keep accurate time, you need water to flow at a constant rate. Not fast, not slow, constant. And the simplest way to get a constant flow is to keep the water level in your supply tank at a constant height, because the pressure at the bottom of a tank depends on how deep the water is above it. More depth, more pressure, faster flow. Less depth, less pressure, slower flow. So if the level drops, your clock starts running slow. If it rises, your clock runs fast. The solution was elegant. You put a float in the tank, literally a thing that floats on the surface of the water. As the water level drops, the float drops, and it's connected to a valve that opens wider, letting more water in. As the water level rises, the float rises, and the valve closes down. The system balances itself. It finds its own equilibrium. Nobody has to stand there watching the water level and turning a tap. The mechanism does it automatically. Now think about what's actually happening here, because this is the seed of everything. There's a desired condition, the water level you want. There's a measurement. The float tells you where the water actually is. There's a comparison, the difference between where the water is and where you want it. And there's a correction. The valve opens or closes to fix the difference. Desired state, measurement, comparison, correction. That loop, that cycle, is the fundamental architecture of every control system ever built. It has a name, and you've probably heard it even if you've never studied engineering. It's called feedback. The output of the system, the water level, is fed back to the input, the valve, to keep things on track. And honestly, that float valve in an ancient water clock is not so different in principle from the float valve in the tank on the back of your toilet. Thousands of years of engineering progress, and we're still using the same basic trick to keep a water level steady. That should tell you something about how powerful and fundamental this idea is. But let's jump forward quite a bit. Because the next really important chapter in the control system story happens in a place you might not expect. 18th century England, in the smoky, clanging world of the Industrial Revolution. And it involves a man whose name you probably know, even if you're not sure exactly why. James Watt. Now, Watt didn't invent the steam engine. That's a common misconception. Steam engines existed before him. Thomas Newcomen had built practical steam engines decades earlier, big lumbering things used mostly to pump water out of mines. What Watt did, starting in the 1760s, was make the steam engine dramatically more efficient and more practical. He introduced the separate condenser, which was a huge thermodynamic improvement. But here's what matters for our story. Watt had a problem. His improved engines were being used not just to pump water, but to drive machinery in factories, mills, looms, all sorts of things. And those machines needed the engine to run at a steady speed. If the engine ran too fast, things could break, or the product would be ruined. Too slow, and production suffered. And the speed of a steam engine depends on the load, how much work it's being asked to do at any given moment. Add more looms to the drive shaft, and the engine slows down. Take some off, and it speeds up. The engine doesn't know what you want. It just responds to the physics of the situation. Watt needed a way to keep the engine speed constant, automatically, without someone standing there all day with their hand on the steam valve. And around 1788, he adapted a device that had been used in simpler forms in windmills, a thing called a centrifugal governor. And this device is so important, so central to the history of control systems, that we should really take our time with it. Picture this. You've got a vertical spindle, a shaft that spins, and it's connected to the engine's output, so it spins at the same rate as the engine. Mounted on this spindle are two heavy metal balls attached by arms that can swing outward. As the spindle spins faster, centrifugal force, or if you want to be physics precise, the tendency of the balls to travel in a straight line, pushes the balls outward and upward. As it spins slower, gravity pulls them back down and inward. The arms the balls are mounted on are connected, through a clever linkage, to the steam valve that controls how much steam gets into the engine's cylinder. So, here's what happens. If the engine speeds up, say because someone disconnected a loom and the load got lighter, the spindle spins faster, the balls fly outward, and through the linkage, they partially close the steam valve. Less steam, less power, the engine slows back down. If the engine slows down, heavier load, the balls drop inward, the linkage opens the steam valve wider, more steam flows, more power, and the engine speeds back up. The system is self-correcting. It's hunting for a balance point, constantly, mechanically, without any human intervention. And here's what's really clever about it. The measurement and the correction are happening through the same physical mechanism. The spinning of the balls is both the sensor and the actuator, linked together in one continuous mechanical loop. It's feedback, just like the float valve, but now it's controlling something much more dynamic. The rotational speed of a powerful engine driving an entire factory. Watt's governor worked beautifully in practice, and it spread everywhere. By the early 1800s, you could hardly find a steam engine without one. Those spinning balls became an icon of the industrial age. If you've ever seen old illustrations of steam engines, you've probably seen the governor sitting on top, its balls whirling around. It became so associated with the idea of regulation and control that the word governor entered everyday language. It's why we sometimes call a person in charge a governor. The device gave its name to the concept. But here's where the story gets deeper, and honestly, This is where it starts to get really interesting from an intellectual standpoint. The governors worked, mostly, but they didn't always work well. Some engines with governors would settle into a nice steady speed, smooth and reliable. Others would develop this annoying tendency to oscillate. The speed would swing up and down, rhythmically, never quite settling. The balls would swing out, the valve would close, the engine would slow, the balls would drop, the valve would open, the engine would speed up, the balls would swing out again, around and around, hunting but never finding. Engineers called this hunting, and it was a real problem. Some governors hunted a little, some hunted a lot, and some were so badly behaved that they were practically useless. And here's the thing. The engineers building these governors didn't really have a systematic way to understand why some worked and some didn't. They could tinker. They could make the balls heavier, or change the length of the arms, or adjust the linkage ratios. And sometimes that helped, and sometimes it made things worse. It was trial and error, craft knowledge, gut feeling. There was no theory. Nobody had written down the mathematics of what was actually happening in that feedback loop. That changed in 1868, when a man named James Clerk Maxwell, yes, the same Maxwell famous for unifying electricity and magnetism, one of the most brilliant physicists who ever lived, published a paper called On Governors. And this paper is remarkable. Maxwell looked at the governor not as a mechanical device to be tinkered with, but as a mathematical system to be analyzed. He wrote down the differential equations that described the motion of the governor and the engine together as a coupled system. And then he asked a very precise question. Under what conditions will this system be stable? Stable, in this context, means that if you disturb it, give the engine a little kick, change the load suddenly, the system will return to its steady state. It'll correct itself and settle down. Unstable means the opposite. A small disturbance gets amplified, the oscillations grow, and the system goes haywire. And the boundary between stable and unstable, Maxwell showed, depends on the specific values of the physical parameters, the mass of the balls, the friction in the linkage, the responsiveness of the steam valve, the inertia of the engine. Change those parameters, and you can cross from stable to unstable territory. This was a huge insight. For the first time, someone had taken a practical engineering problem. Why does my governor hunt? And turned it into a mathematical question with a precise answer. You don't have to guess anymore. You can calculate. You can predict before you build the thing, whether it's going to behave itself or oscillate wildly. That's the power of theory. It turns craft into science. Maxwell's paper was dense and not easy reading, even for mathematicians of his era. He analyzed several specific types of governors, worked out the stability conditions for each, and showed that the question of stability comes down to the roots of a certain polynomial equation, the characteristic equation of the system. If all the roots of that equation have negative real parts, the system is stable. If any root has a positive real part, the system is unstable. Now, that language might sound abstract, but let me put it in plain terms. The characteristic equation is basically a mathematical summary of all the competing tendencies in the system, the things that push it back toward equilibrium, and the things that push it away. The roots of the equation tell you which tendencies win. Negative roots mean the corrective forces dominate, disturbances die out. Positive roots mean the destabilizing forces dominate, disturbances grow. And Maxwell realized something frustrating. For simple systems, second-order equations, meaning systems described by two key variables, you could figure out the stability pretty easily just by looking at the coefficients. But for more complex systems, third order, fourth order, higher, it got really hard to determine whether all the roots had negative real parts without actually solving the equation. And solving high-order polynomial equations analytically is, in general, impossible. There's no formula, no shortcut. Maxwell essentially posed this as an open problem. Can someone find a way to determine the stability of a system without having to solve the characteristic equation? That challenge sat there for about a decade before someone picked it up. And the person who did was not a physicist or an engineer, but a mathematician, Edward John Routh, working at Cambridge. In 1877, Routh submitted an essay for the Adams Prize that laid out a systematic method for determining whether all the roots of a polynomial have negative real parts, using only the coefficients of the polynomial. You didn't have to find the roots. You just had to arrange the coefficients in a specific table, now called the Routh array, and check a simple set of conditions. If all the entries in the first column of the table were positive, the system was stable. If any were negative or zero, it wasn't. This was exactly what Maxwell had asked for, a practical, mechanical procedure that any engineer could follow. You write down your characteristic equation, you build the Routh array, you check the signs, and you know, definitively, mathematically, whether your system will be stable or not. No guessing, no trial and error, no building a prototype, and hoping for the best. And here's a lovely detail. A few years later, in 1895, a German mathematician named Adolf Hurwitz independently arrived at essentially the same result, using a slightly different approach, determinants of matrices rather than Routh's tabular method. The two methods are mathematically equivalent, and today the stability criterion is usually called the Routh-Hurwitz criterion, honoring both of them. It's one of those cases in the history of science where two people, working independently in different countries, converge on the same truth, which usually means the idea was ripe, the question was in the air, and the tools were ready. So by the end of the 19th century, we had something genuinely new. We had the concept of feedback, ancient, intuitive, embodied in float valves and spinning governors. And we had the beginnings of a mathematical framework for analyzing feedback systems, for predicting whether they'd behave or misbehave. The practical and the theoretical were starting to come together. But the real explosion of control theory, the period when it went from a niche academic topic to one of the most important branches of engineering in the world, was still ahead. It was going to be driven by a completely different technology, one that had nothing to do with steam engines or spinning balls. It was going to come from the telephone, of all things, from the problem of sending a human voice across a continent through a wire, and from a quiet, extraordinarily brilliant engineer working at Bell Telephone Laboratories in the 1920s, a man named Harold Stephen Black, who had an idea on a ferry boat one summer morning that would change the way engineers thought about feedback forever. It was the summer of 1927, and Black was riding the Lackawanna Ferry from his home in New Jersey across the Hudson River to his office at Bell Labs in Lower Manhattan. He'd been wrestling with a problem for years, literally years, and on that particular morning, something clicked. He grabbed the only piece of paper he had on him, which happened to be a copy of the New York Times, and right there on the margin of the newspaper, he sketched out the essential idea of the negative feedback amplifier. That sketch, scrawled on newsprint on a ferry boat, would become one of the most important inventions in the history of electronics. But to understand why it mattered so much, you need to understand the problem he was trying to solve. Here's the situation. By the 1920s, the telephone network was expanding rapidly across the United States. The dream was coast-to-coast calling, a person in New York picking up the phone and talking to someone in San Francisco, their voice traveling nearly 3,000 miles through copper wire. The problem was that electrical signals weaken as they travel through wire. They lose energy. The farther the signal goes, the fainter it gets. By the time a voice signal had traveled a few hundred miles, it was basically inaudible. So you needed amplifiers, vacuum tube amplifiers, which were the technology of the day, placed at regular intervals along the line to boost the signal back up. For a transcontinental telephone line, you might need dozens of these amplifier stages, maybe more, each one taking the weakened signal and pumping it back up to a usable level. Now, here's where the trouble starts. Vacuum tube amplifiers weren't perfect. They introduced distortion. Every time the signal passed through an amplifier, it got a little bit mangled. The waveform that came out wasn't quite the same shape as the waveform that went in. For a single amplifier, the distortion was small, maybe barely noticeable. But remember, you're chaining dozens of these amplifiers together in series. Each one adds its own little bit of distortion. And distortion compounds. It's like making a photocopy of a photocopy of a photocopy. Each generation degrades the quality a little more, and after enough generations, the original is unrecognizable. After passing through 20 or 30 amplifiers, a human voice would come out the other end, garbled, noisy, and unintelligible. The signal was loud enough. That wasn't the problem. The problem was that it didn't sound like a human voice anymore. So Bell Labs had this enormous engineering challenge. They needed amplifiers with much, much less distortion. And the obvious approach was to try to build better amplifiers, more linear vacuum tubes, more carefully designed circuits. Engineers spent years on this, and they made progress, but they kept hitting fundamental limits. Vacuum tubes are inherently non-linear devices. You can improve them, but you can't make them perfect. And when you need to chain dozens of them together, even tiny imperfections add up to a big problem. It seemed like there was a hard wall, a physical limit to how good you could make the system. This is what Harold Black had been thinking about, obsessively, for years. And the idea that came to him on that ferry, it was counterintuitive. Genuinely counterintuitive, to the point that when he first presented it, many of his colleagues thought he was wrong. Some thought he was crazy. The idea was this: instead of trying to make each amplifier perfect, what if you deliberately took some of the amplifier's output, fed it back to the input, and subtracted it? What if you used negative feedback? Think about what that means for a second. You have an amplifier that's producing a strong output signal. You take a fraction of that output, flip its sign, make it negative, and mix it back into the input. What happens? Well, the overall gain of the amplifier drops. You're fighting against yourself. You're deliberately reducing the amplification. That seems like exactly the wrong thing to do, right? You need these amplifiers to boost the signal, and now you're proposing to make them weaker. But here's what's clever. Here's what Black realized. When you apply negative feedback, you don't just reduce the gain, you also reduce the distortion by roughly the same factor. And this is the key insight. You can always get more gain. Gain is cheap. You can add more vacuum tubes, more amplifier stages. What you can't easily get, what was the scarce resource, was linearity, fidelity, accuracy. And negative feedback lets you trade away gain you don't need in exchange for linearity you desperately do need. It's like a bargain, a trade. You give up something abundant to get something rare. Let me put it another way. Say your amplifier has a gain of 10,000. It multiplies the signal by 10,000, but it introduces 1% distortion. Now you apply negative feedback that reduces the gain by a factor of, say, 50. Your new gain is only 200, but your distortion also drops by roughly a factor of 50, down to about 0.02%. And if you need more total gain, you just add another amplifier stage. The distortion stays tiny. You've solved the problem not by making a better amplifier, but by making a clever system out of an imperfect amplifier. You've used the structure of the system, the feedback loop, to compensate for the flaws of the components. This is a profound idea, and it goes way beyond telephone amplifiers. It's really one of the deepest ideas in all of engineering. You don't need perfect parts if you have the right architecture. The system can be better than its components. That's what feedback buys you. Now, Black filed his patent in 1928, but it took 9 years. 9 years for the patent to be granted in 1937. Part of the reason for the delay was that the patent examiners simply didn't believe the claims. The idea that you could reduce distortion by feeding the output back to the input and subtracting seemed to violate something fundamental. It felt like getting something for nothing. Some examiners compared it to perpetual motion claims. Black later said that the patent office treated his application with about the same skepticism they'd give to a perpetual motion machine. But it worked. It demonstrably, measurably worked. And once Bell Labs started building negative feedback amplifiers into the telephone network, the improvement in call quality was dramatic. But here's the thing about negative feedback, and this connects directly back to everything we were talking about earlier with governors and Maxwell and Routh. Negative feedback can make a system beautifully stable and well-behaved. But if you get the design wrong, if the gain is too high, or if there are time delays in the feedback path, or if the phase of the signal shifts in the wrong way, negative feedback can turn into positive feedback at certain frequencies. And when that happens, the system doesn't just perform poorly. It oscillates. It howls. It becomes unstable. Anyone who's ever heard the shriek of a microphone placed too close to a speaker has heard positive feedback in action. That's a feedback loop where the output, the sound from the speaker, gets picked up by the input, the microphone, and amplified again and again and again, each cycle getting louder until the system is screaming at you. So the same fundamental question that Maxwell had asked about steam governors in 1868, will this feedback system be stable, was now urgently relevant to electronic amplifiers. And it needed to be answered in a much more sophisticated way, because electronic systems operate across a wide range of frequencies, and the behavior of the amplifier and the feedback path changes with frequency. A system might be stable at low frequencies, but unstable at high frequencies, or vice versa. You needed tools that could handle this frequency-dependent behavior. And this is where another Bell Labs engineer enters the story, a man named Harry Nyquist. Nyquist was a Swedish-born electrical engineer, quiet, methodical, deeply mathematical. He'd been at Bell Labs since the early 1920s, working on telegraph and telephone theory, and he'd already made major contributions to communication theory. In 1932, Nyquist published a paper called Regeneration Theory that tackled exactly this problem. He asked, given a feedback amplifier where the gain and phase shift vary with frequency, how do you determine whether the system will be stable? Nyquist's approach was elegant and, honestly, kind of beautiful once you see it. Instead of trying to find the roots of the characteristic equation, which is what Routh and Hurwitz had done, and which works fine for simple systems, but becomes incredibly unwieldy for complex ones, Nyquist used a graphical method. He said, "Look, at each frequency, your amplifier's feedback loop has a certain gain and a certain phase shift. You can represent that as a point on a graph, what we now call the complex plane, where one axis represents the real part and the other represents the imaginary part. As you sweep through all frequencies from 0 to infinity, that point traces out a curve, a closed curve, a loop, a shape." Nyquist showed that you can determine the stability of the entire system just by looking at the shape of that curve and asking one question: does it encircle a specific critical point on the graph? That's it. That's the Nyquist stability criterion. You don't need to solve any polynomial equations. You don't need to find any roots. You just need to look at a curve and see whether it wraps around a particular point. For a working engineer in the 1930s, this was incredibly powerful, because you could actually measure the gain and phase of a real amplifier in the lab. You didn't need a perfect mathematical model. You could plot the data, draw the curve, and read off the stability answer directly from the picture. And almost immediately after Nyquist, another Bell Labs engineer, the place was just overflowing with talent. A man named Hendrik Bode took these ideas even further. Bode, whose name is pronounced Bode, even though everyone wants to say Bode like the English word, developed a different but related graphical technique. Instead of Nyquist's single curve on the complex plane, Bode split the information into two separate plots, one showing how the gain varies with frequency and another showing how the phase shift varies with frequency. These are the famous Bode plots that every electrical engineering and control systems student learns to draw, and they're remarkable because they make complex system behavior visually intuitive. You can look at a Bode plot and see, almost at a glance, how much margin of safety a system has before it goes unstable. Bode formalized this with concepts he called gain margin and phase margin. Essentially, how close is the system to the edge of instability? How much could conditions change before things go wrong? Think about what had happened in just a few years at this one laboratory. Black invents the negative feedback amplifier. Nyquist figures out how to determine whether a feedback system is stable using a graphical method based on frequency response. Bode develops practical plotting tools that make stability analysis something an engineer can do at their desk with a slide rule and a sheet of graph paper. 3 interlocking contributions, each building on the others, all coming out of the same hallways at Bell Labs in the 1930s. It's one of those extraordinary concentrations of genius and practical need that occasionally happens in the history of technology, where the right people are in the right place, working on the right problem at exactly the right time. And all of this was about to become even more urgent because the world was sliding toward war. And war, as it so often does in the history of engineering, was about to accelerate everything. The problem that would push control theory from the telephone lab into the center of military technology was one that sounds simple, but turned out to be ferociously difficult. How do you aim a gun at an airplane that's moving at 300 miles per hour through 3-dimensional space, when the shell you're firing takes several seconds to reach the altitude where the plane is flying, and by the time it gets there, the plane has moved hundreds of feet from where it was when you pulled the trigger? That problem, the fire control problem, was about to reshape everything. And the people who would tackle it were about to discover that the mathematics Black, Nyquist, and Bode had developed for telephone amplifiers was exactly, almost eerily, the right framework for aiming guns at fast-moving targets in the sky. Let's slow down and really think about what made this problem so hard, because it's one of those things that seems like it should be straightforward until you start pulling it apart. You're standing on the deck of a ship, or you're at an anti-aircraft battery on the ground, and there's a plane coming toward you. You can see it. You know roughly where it is. You have a gun that can throw a shell up to that altitude. So just point the gun at the plane and fire, right? Except no, not even close, because that shell takes time to travel. If the plane is at 20,000 feet, your shell might take 5, 6, 7 seconds to reach that altitude depending on the weapon. And in 7 seconds, a plane moving at 300 miles per hour has traveled over 3,000 feet, more than half a mile. So you can't aim at where the plane is. You have to aim at where the plane is going to be when the shell arrives. You're shooting at a point in empty sky and hoping the plane flies into your shell at exactly the right moment. Now, that alone would be hard enough if the plane were flying in a straight line at a constant speed. You could do the geometry, calculate the lead angle, and fire. Gunners had been doing versions of that since the First World War, but planes in the Second World War weren't flying in straight lines. They were maneuvering. They were diving, climbing, banking, changing speed. The target was performing what engineers would call a non-stationary process. Its future position couldn't be perfectly predicted from its past behavior because the pilot was actively making decisions to evade you. So you had this deeply layered problem. You needed to track the plane's current position accurately. You needed to predict its future position based on its recent trajectory. You needed to calculate the firing solution, the angle and timing that would put the shell at that predicted position. And you needed to do all of this continuously, in real time, updating your prediction and your aim as new information came in, because the plane's behavior was constantly changing. This is a control problem, a feedback control problem. You observe, you predict, you act, you observe the result, you correct, you act again. And here's where a mathematician named Norbert Wiener enters the story, and things get fascinating. Wiener was at MIT, and he was one of the most brilliant and eccentric figures in 20th century mathematics. He'd been a child prodigy, entered college at 11, had his PhD from Harvard by 18. By the time the war came, he was in his mid-40s, a stocky, nearsighted man who was famously absent-minded. There are stories about Wiener wandering the halls of MIT, stopping students to ask them which direction he'd been walking when they encountered him. Because if he'd been walking toward his office, then he'd already had lunch. But if he'd been walking away from it, then he hadn't. Whether that particular story is true or embellished, it captures something real about the man. His mind was almost entirely consumed by abstract thought, and the mundane details of physical existence were a persistent inconvenience. But Wiener was also deeply motivated by practical problems when they were interesting enough, and the fire control problem was very interesting. In 1940, he began working on it, collaborating with a young engineer named Julian Bigelow. And the insight that Wiener brought, the thing that made his approach different from the purely mechanical fire control computers that already existed, was that he treated the entire system, including the human operator, as a single feedback loop. Think about what happens when a gunner is tracking a plane through a gun sight. The gunner sees the plane, turns a hand wheel to move the gun, watches the sight to see if the gun is now pointing at the plane, adjusts again. That's a feedback loop with a human being as one of the components. And here's the thing that Wiener realized. The human introduces errors, not because the gunner is bad at the job, But because human muscles have lag, human perception has noise, human reactions have delay. The gunner's hand trembles. The gunner overcompensates, then corrects back. These errors aren't random in the way that, say, radiostatic is random. They have structure. They have patterns that relate to the dynamics of the human neuromuscular system. Wiener's radical idea was to model the human operator statistically, to treat the gunner's tracking errors as a stochastic process, a signal corrupted by noise, and to design a filter that could extract the best prediction of the target's future position from the noisy, delayed, imperfect data that the human-machine system was producing. This was extraordinary. He was applying the mathematics of communication theory, the same kind of thinking that was happening at Bell Labs, to the problem of prediction and control. And the result was a classified document that Wiener and Bigelow produced in 1942, formally titled The Extrapolation, Interpolation, and Smoothing of Stationary Time Series, but universally known as the Yellow Peril because of its bright yellow cover and because it was so mathematically dense that even experienced engineers found it nearly impenetrable. The Yellow Peril was, in a practical sense, not a huge success. The filters Wiener designed were theoretically optimal, but very difficult to implement with the analog computing hardware available during the war. The actual fire control systems that saw widespread use, like the famous SCR-584 radar coupled with the M9 gun director, used somewhat simpler prediction methods. But conceptually, what Wiener had done was enormous. He had connected feedback control, statistical prediction, communication theory, and human factors into a single mathematical framework. He was seeing something that almost nobody else saw at that point. That all of these problems were fundamentally the same problem. Controlling a gun, filtering noise from a signal, predicting the future state of a system. These were all manifestations of the same underlying mathematics. And here's where something beautiful happens in the history of ideas. While Wiener was working on prediction and fire control at MIT, over in the classified world of military research, other engineers were attacking related problems from different angles. At Bell Labs, the same Bell Labs where Black and Nyquist and Bode had done their work, a team was developing electrical gun directors and dealing with the same questions of feedback, stability, and noise. The frequency domain tools that Bode had created for amplifier design turned out to be directly applicable to servo mechanisms, the motor-driven positioning systems that aimed guns and turned radar dishes. A servo mechanism is just a feedback control system where the output is a mechanical position. You command a position, a sensor measures the actual position, the error drives a motor, and the motor moves until the error is zero. Same structure as Black's amplifier, same stability concerns, same mathematics. This convergence was formalized in an extraordinary way. In 1943 and 1944, a group of researchers organized what became known as the Servo Conferences, classified meetings where people from MIT's Radiation Laboratory, Bell Labs, and other research groups came together to share their work. And what they discovered was that they'd all been independently developing the same ideas. The language was different. The Bell Labs people talked about feedback amplifiers. The MIT people talked about servo mechanisms. The fire control people talked about tracking loops. But the mathematics underneath was identical. Transfer functions, frequency response, stability criteria, feedback. It was all the same theory wearing different hats. Out of this wartime convergence came a remarkable textbook. In 1945, a trio of authors, Hubert James, Nathaniel Nichols, and Ralph Phillips, published Theory of Servo Mechanisms, which was essentially the declassified version of the wartime research. This book, along with a few others from the same period, became the foundation of what we now call classical control theory. And the key insight it codified was this: you can analyze and design any feedback control system using the same set of tools, regardless of whether the system is an amplifier, a gun turret, an autopilot, or an industrial process controller. The transfer function is the universal language. The Bode plot, the Nyquist plot, the root locus. These are the universal tools. The physics of the specific system determines the particular transfer function, but once you have that transfer function, the analysis and design methods are the same across every domain. Now, I want to come back to something, because there's a concept that came out of this wartime work that's so fundamental to control systems that it's worth really sitting with. It's the concept of the PID controller, proportional, integral, derivative control. And while PID controllers actually predate the war, they were being used in industrial process control in the 1930s, and two engineers named John Ziegler and Nathaniel Nichols published their famous tuning rules in 1942. It was during and after the war that the theoretical understanding of why PID works really crystallized. Here's the idea, and it's beautifully intuitive once you see it. You have a system and you want it to track some desired value, a temperature, a position, a speed, whatever. You measure the error, which is just the difference between what you want and what you've got. Now, what do you do with that error? The simplest thing is proportional control. You apply a correction that's proportional to the error. Big error, big correction. Small error, small correction. Makes sense, right? And it works, mostly. But it has a problem. In many systems, proportional control alone leaves you with a persistent small error. The system gets close to the target, but never quite reaches it. There's always a little offset. It's like trying to hold a heavy door open with a spring. The spring pulls the door toward closed, and you push it toward open, and it settles at some compromise position that's neither fully open nor fully closed. So you add the integral term. The integral of the error is basically the accumulated error over time. If there's been a small positive error persisting for a long time, that integral grows and grows, and it drives an increasing correction that eventually eliminates the offset. It's like the system is getting increasingly impatient with any persistent error. The longer the error lasts, the harder the integral term pushes to fix it. Beautiful. But now you've introduced a new problem. The integral term can build up too much momentum. It can push past the target and overshoot, then overcorrect the other way, and you get oscillation, which is where the derivative term comes in. The derivative of the error is the rate of change of the error, how fast the error is changing right now. If the error is shrinking rapidly, the derivative term says, ease off. You're approaching the target fast. Don't overshoot. If the error is growing rapidly, the derivative term says, push harder. Things are getting worse quickly. It's anticipatory. It's looking at the trend, not just the current state. It's the difference between a driver who only looks at how far they are from the center of the lane versus a driver who also notices which direction the car is drifting. That anticipation is what makes the system respond smoothly instead of lurching back and forth. 3 terms: proportional, integral, derivative, each addressing a different aspect of the error, its current magnitude, its accumulated history, its rate of change. Together, they give you a controller that can handle a remarkable range of situations. And here's what's truly astonishing about PID control. Despite all the sophisticated control theory that has been developed in the decades since, optimal control, adaptive control, robust control, model predictive control, all of these advanced techniques, the PID controller remains to this day the most widely used controller in the world. Something like 90% or more of all industrial control loops use some form of PID. The thermostat concept in your house, the cruise control in your car, the temperature regulation in a chemical reactor, the position control in a robotic arm. PID is everywhere. It's the workhorse of the control world, and it works so well in so many situations that there's often no reason to use anything more complicated. But the story of control theory didn't stop with PID and frequency domain methods, because there was a whole class of problems that classical control theory struggled with. And to understand what those problems were and how they got solved, we need to travel from the laboratories of wartime America and Britain to a somewhat unexpected place, the Soviet Union in the 1950s, where a mathematician named Lev Pontryagin was about to change the game entirely. Pontryagin was blind. He had been since the age of 14, when a stove exploded and took his sight. And yet he became one of the most brilliant mathematicians of the 20th century, working almost entirely through mental visualization and the help of his mother, who read mathematical papers aloud to him for years, and later through students and colleagues who served as his eyes on the page. Think about that for a second. This is a man doing cutting-edge topology and differential equations in his head, building geometric intuitions about spaces most sighted mathematicians struggle to picture even with paper and pencil in front of them. And it was this extraordinary mind that turned its attention in the mid-1950s to a question that classical control theory couldn't really answer well. The question was this: what is the absolute best you can do? C. Classical control, the Bode plots, the Nyquist diagrams, the PID tuning rules we just talked about. Those tools are fantastic for analyzing a system and adjusting it until it behaves well. You look at your gain margin, you tweak your controller gains, you check the step response, and you iterate until the system is stable and performs acceptably. But acceptably is not the same as optimally. Classical methods can tell you whether a given controller will be stable. They can help you shape the frequency response to get decent performance. But they don't tell you, out of all possible control strategies, which one is the best. They don't give you the mathematically optimal solution. And for certain problems, optimal really matters. The problem that brought this into sharp focus wasn't industrial temperature control or telephone amplifier design. It was rockets. Specifically, the question of how to steer a rocket or a missile so that it reaches its target using the minimum amount of fuel or in the shortest possible time or with the greatest accuracy. This was the late 1950s, remember. The space race was heating up. Both the Soviet Union and the United States were pouring enormous resources into rocketry and missile guidance, and the control problems involved were fundamentally different from anything a PID controller was designed to handle. Here's why. A rocket burning fuel is a system whose mass is changing as it flies. The dynamics are nonlinear. The environment changes as it climbs through the atmosphere. Air density drops, gravity shifts slightly. The vehicle gets lighter as propellant burns away. And you don't just want the rocket to be stable. You want it to follow a very specific trajectory that minimizes fuel consumption, because every kilogram of fuel you save is a kilogram of payload you can carry to orbit. This is an optimization problem wrapped inside a control problem, and the classical frequency domain tools just weren't built for it. Now, optimization itself wasn't new. The calculus of variations, which deals with finding functions that minimize or maximize some quantity, goes back to the 1700s. Euler, Lagrange, those giants. If you've ever seen the brachistochrone problem, the question of what curve a bead should slide along to get from one point to another in the shortest time, that's calculus of variations. Beautiful mathematics. But the classical calculus of variations had a limitation that mattered enormously for control problems. It didn't handle constraints on the control input very well. And real control systems always have constraints. A rocket engine can only produce so much thrust. A control surface can only deflect so many degrees. A valve can only open so far. You can't just compute some mathematically elegant optimal trajectory and then discover that it requires infinite thrust at some point. That's useless. This is exactly where Pontryagin came in. Working with his students, particularly Vladimir Boltiansky and Revaz Gamkrelidze, Pontryagin developed what he called the maximum principle, published in its full form around 1956 to 1958. And what the maximum principle does is give you the necessary conditions for an optimal control strategy when you have hard constraints on your control inputs. It tells you, given a system described by differential equations, given a performance criterion you want to optimize, and given bounds on what your control input is allowed to do, here is what the optimal control must look like. The mathematical details are deep, but the core idea is surprisingly elegant. You introduce what are called cost-state variables. Think of them as shadow prices, if that helps. For every state variable in your system, position, velocity, mass, whatever describes your system, there's a corresponding cost-state variable that captures how valuable a small change in that state would be for your overall objective. And the optimal control at every instant is the one that maximizes a special function called the Hamiltonian, which combines the system dynamics, the cost you're trying to minimize, and these cost-state variables. If you've encountered Hamiltonian mechanics in physics, that's not a coincidence. The mathematical structure is deeply related. Here's what's really clever about this. Because of the constraints on the control input, the optimal solution often turns out to be what's called bang-bang control. The control input slams to one extreme or the other, full thrust or no thrust, hard left or hard right, and switches between these extremes at specific moments. That might sound crude, but it's mathematically provable that for many systems, this is genuinely the best you can do. If you're trying to move a satellite from one orbit to another in minimum time with a thruster that's either on or off, the optimal strategy really is to fire at full blast, coast, then fire again. The maximum principle tells you exactly when to switch. Now, at roughly the same time, Pontryagin was developing the maximum principle in Moscow. An American mathematician named Richard Bellman, working at the Rand Corporation in Santa Monica, California, was attacking the same class of problems from a completely different angle. And this is one of those wonderful moments in the history of science where two people, working independently in different countries, with different mathematical traditions, converge on complementary solutions to the same fundamental problem. Bellman's approach was called dynamic programming. And while Pontryagin maximum principle works forward through time, setting up a boundary value problem that you solve to find the optimal trajectory, Bellman's dynamic programming works backward. The core insight, Bellman called it the principle of optimality, is almost deceptively simple when you hear it. It says, whatever your current state is, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. In plain language, If you're on the optimal path, then from any point along that path, the rest of the path must also be optimal. You can't be on the best overall route if you're making suboptimal choices from where you currently stand. This sounds almost obvious when you say it out loud, but it's incredibly powerful as a computational principle. It means you can break a complex optimization problem into a sequence of simpler ones, working backward from the end. What's the best thing to do in the last step? Okay. Given that, what's the best thing to do in the second to last step? And so on, all the way back to the beginning. Bellman formalized this with what's now called the Hamilton-Jacobi-Bellman equation, a partial differential equation that the optimal cost to go must satisfy. There's a wonderful story about the name dynamic programming. Bellman himself explained it later. He was working at RAND, which was funded by the Air Force, and the Secretary of Defense at the time was Charles Wilson, who Bellman described as having a pathological fear and hatred of the word research. Bellman needed a name for his work that would shield it from political hostility. Programming was already an acceptable word in military circles. It just meant planning or scheduling, as in linear programming. And dynamic? Bellman said he chose it because it sounded impressive, had no precise meaning that a congressman could object to. And here's the kicker, it's impossible to use the word dynamic in a pejorative sense. So the name was partly a political camouflage. That's the kind of thing that happened in Cold War research. But anyway, the point is that by the late 1950s, you had these two powerful frameworks, Pontryagin's maximum principle and Bellman's dynamic programming, that could handle optimal control problems that classical methods couldn't touch, and both of them shared a crucial feature that distinguished them from the classical Bode-Nyquist PID approach. They worked in the time domain with state variables rather than in the frequency domain with transfer functions. This was a fundamental shift, and the person who really crystallized this shift, who built it into a coherent framework that engineers could actually use for practical systems, was Rudolf Kalman. If Pontryagin and Bellman laid the mathematical foundations, Kalman built the house that engineers moved into. Kalman was born in Budapest in 1930, emigrated to the United States, and did his graduate work at MIT and Columbia. And in a remarkable burst of papers between about 1958 and 1964, he essentially created what we now call modern control theory, or state space control theory. Here's the key idea. Instead of describing a system by its transfer function, that input-output relationship in the frequency domain, Kalman said, let's describe it by its state. The state of a system is the minimum set of variables that, together with the future inputs, completely determines the future behavior of the system. For a simple mass on a spring, the state is the position and the velocity. If you know those two numbers right now, and you know what forces will be applied in the future, you can predict everything about the system's motion from this moment forward. You don't need to know the entire past history. The state captures everything relevant about the past in a compact set of numbers. This is a profound idea, and it connects to something deep in physics and information theory. The state is, in a sense, the system's memory. And Kalman showed that you could write the dynamics of a huge class of systems, linear systems specifically, in a beautifully compact matrix form. The state evolves according to a matrix equation. The rate of change of the state equals a matrix times the current state, plus another matrix times the control input. The output you can measure equals yet another matrix times the state. That's it. 3 matrices, A, B, and C, and you've captured the entire dynamics of the system. If you've ever seen the notation x dot equals AX plus BU, Y equals CX, That's Kalman's state space formulation, and it's the backbone of modern control theory. Now you might be thinking, okay, that's a neat way to write things down, but what does it buy you? And the answer is everything. Because once you have the system in state space form, you can ask questions that are almost impossible to formulate in the frequency domain. Questions like, is this system controllable? Meaning, can I actually steer the state from any initial condition to any desired final condition using the available inputs? And is it observable? Meaning, can I figure out what the internal state is just by watching the outputs? These are fundamental questions about the structure of the system, and Kalman gave precise mathematical conditions for answering them. A matrix rank test. You build a specific matrix from A and B, and if it has full rank, the system is controllable. Another matrix from A and C tells you about observability. This matters enormously in practice. Imagine you're designing a controller for an aircraft. The aircraft has many state variables: speeds, angles, angular rates, positions, but you can only measure some of them directly. Maybe you have an accelerometer and a gyroscope, but you can't directly measure the angle of sideslip. Kalman's observability condition tells you whether it's theoretically possible to reconstruct that unmeasured state from the measurements you do have. If the system is observable, you can build what's called an observer, a mathematical model running alongside the real system that estimates the states you can't measure. And if it's not observable, no amount of clever engineering will let you estimate those hidden states from your available sensors. You need a different sensor, or you need to accept that some information is simply inaccessible. And then there's the result that really made Kalman famous beyond the control theory community, the one that arguably had the single greatest practical impact of any result in modern control theory. In 1960, Kalman published a paper titled A New Approach to Linear Filtering and Prediction Problems. And in that paper, he introduced what the world now calls the Kalman filter. Remember Wiener's work during the war, the Yellow Peril? Wiener had solved the optimal filtering problem, how to extract a signal from noise, but his solution required you to know the entire statistical history of the signal, and it produced a filter that was fixed, time invariant, and worked in the frequency domain. It was mathematically beautiful, but practically difficult to implement, especially for systems whose characteristics changed over time. Kalman attacked the same problem but from the state space perspective, and his solution was recursive. Instead of needing the entire history of measurements, the Kalman filter updates its estimate one step at a time. A new measurement comes in, you blend it with your prediction based on the system model, and you get an updated estimate. The filter automatically adjusts how much it trusts the measurement versus the model prediction, based on the relative uncertainties of each. When your sensors are noisy but your model is good, it leans on the model. When your model is uncertain but your sensors are precise, it leans on the measurements. It finds the optimal balance. In a precise mathematical sense, it minimizes the expected squared error of the estimate. And here's where this story takes a turn that connects it to one of the most dramatic engineering achievements in human history, because the Kalman filter is what made the Apollo navigation system possible. When Stanley Schmidt at NASA's Ames Research Center heard about Kalman's work in the early 1960s, he realized it was exactly what they needed for the Apollo guidance computer. The spacecraft had an inertial measurement unit, gyroscopes and accelerometers, that would slowly drift over time, accumulating errors. It also had a sextant that the astronaut could use to take star sightings, but those measurements were intermittent and noisy. The Kalman filter could fuse these two sources of information optimally, continuously correcting the inertial navigation errors with the star sightings, running on a computer with less processing power than a modern calculator you'd buy at a drugstore. We're talking about the Apollo guidance computer, which had roughly 2 kilowords of erasable memory. That's it. 2,000 words of working space, essentially. And Schmidt and his team at NASA figured out how to make the Kalman filter run within those constraints, which is an engineering achievement that deserves way more recognition than it gets. Think about what that means practically. You've got 3 astronauts hurtling through space at thousands of miles per hour, and their navigation system is constantly asking 2 questions. Where are we? And where are we going? The inertial measurement unit gives a continuous answer, but that answer drifts. The gyroscopes precess slightly. The accelerometers have tiny biases, and over the course of a 3-day trip to the moon, those tiny errors compound into enormous position uncertainties. Without correction, the spacecraft could miss the moon entirely, or worse, come back at the wrong angle and skip off Earth's atmosphere like a stone off water, or plunge in too steeply and burn up. The margin for the re-entry corridor was shockingly thin, something like plus or minus about half a degree. So navigation accuracy wasn't optional. It was life or death. And the star sightings were the correction mechanism. An astronaut, often the command module pilot, would peer through the spacecraft's sextant, align crosshairs on a known star while simultaneously marking a landmark or the horizon of a celestial body, and the computer would take that angular measurement and feed it into the Kalman filter. Each sighting was a little noisy, a little imperfect, because you're a human being floating in a tin can trying to hold crosshairs steady on a star. But the filter knew how to weigh that imperfect measurement against its current best estimate of the state, and every time it incorporated a new sighting, the uncertainty shrank. The covariance matrix, that's the mathematical object tracking how uncertain the filter is about each component of the state, would tighten up with each measurement, then gradually expand again between measurements as the model uncertainty accumulated, then tighten again with the next sighting. This breathing rhythm of uncertainty, expanding and contracting, is one of the most elegant things about the Kalman filter. It knows what it doesn't know, and it quantifies that ignorance precisely. Now, there's a beautiful detail in the Apollo story that often gets overlooked. The Kalman filter implementation for Apollo wasn't a straightforward textbook application. The state vector they were estimating had something like 9 components, 3 for position, 3 for velocity, and additional error states for the inertial platform. But the computer was so limited that they couldn't maintain and update the full covariance matrix in real time. So Schmidt's group had to develop clever approximations, partitioning the state, simplifying the matrix operations, finding ways to get 95% of the optimal performance with maybe 20% of the computation. That's real engineering, right? The theory says, here's the perfect answer. And the engineer says, great. Now, how do I make it work on this pathetic little computer that has to also run guidance and flight control simultaneously? The gap between theory and implementation is where the art lives, and the Kalman filter worked. It worked on Apollo 8, the first crewed mission to orbit the moon. It worked on Apollo 11, guiding Armstrong, Aldrin, and Collins to the lunar surface and back. It worked on Apollo 13, under conditions nobody had planned for, when the crew had to use the lunar module as a lifeboat, and the navigation problem became enormously more complicated. The filter kept running, kept estimating, kept fusing whatever measurements the crew could provide. There's something deeply reassuring about that. A mathematical algorithm conceived by a Hungarian-American mathematician working in abstract theory, implemented by NASA engineers on primitive hardware, functioning correctly while 3 human lives depended on it 250,000 miles from home. But here's the thing about the Kalman filter that extends far beyond Apollo. Once people saw what it could do, it spread everywhere, and I mean everywhere. Today, the Kalman filter and its descendants are running in your phone right now. Your GPS receiver uses a Kalman filter to fuse satellite signals with accelerometer data to estimate your position and velocity. The autopilot in a commercial aircraft uses Kalman filters, multiple ones actually, to estimate the aircraft's attitude, speed, and position by blending data from inertial sensors, air data probes, GPS, and radio navigation aids. Self-driving cars use extended Kalman filters, or their cousins, unscented Kalman filters, to track the positions of other vehicles and pedestrians. Financial models use Kalman filters. Weather prediction models use them. Robotics, submarine navigation, spacecraft attitude determination. The list is almost absurd in its breadth. It might be the single most widely applied result in all of control theory. Kalman published that paper in 1960, and more than 6 decades later, it's more relevant than ever. So by the mid-1960s, the landscape of control theory had been transformed. You had classical control, Bode plots, Nyquist diagrams, root locus, PID controllers, which was mature, practical, and deeply understood. And now you had modern control, state space models, optimal control via Pontryagin's maximum principle, or Bellman's dynamic programming, and optimal estimation via the Kalman filter. The modern approach was more powerful in many ways. It could handle multiple input, multiple output systems naturally. It could optimize performance criteria explicitly. It could deal with systems that had many interacting state variables. For aerospace applications especially, where you might need to control a vehicle with 6 degrees of freedom simultaneously, state space methods were a revelation. But, and this is a significant but, modern control theory had a problem. A subtle, dangerous problem that took about a decade to fully appreciate. And it had to do with something called robustness. Let me explain what I mean by that. When you design a controller using optimal control theory, you're working with a mathematical model of the system. You write down your A, B, C matrices, you specify your cost function, and the math gives you the optimal controller. Beautiful. Except, your model is never perfect. The real system always differs from the model in ways large and small. Maybe the mass of the aircraft is slightly different than you assumed. Maybe there's an aerodynamic effect you didn't model. Maybe a sensor has a bias you didn't account for. The question is, when the real world deviates from your model, does your controller still work? That's robustness. A robust controller keeps performing adequately even when the model is wrong. A non-robust controller works perfectly in simulation and falls apart in reality. And here's what's wild about this. Classical control, almost by accident, had built-in robustness. When you designed a controller using Bode's frequency response methods, you explicitly looked at gain margin and phase margin. Those were measures of how much the system could deviate from your model before going unstable. Every classical control designer knew to leave adequate margins. It was baked into the methodology. But early modern control theory didn't have equivalent safeguards. You could design a mathematically optimal controller that had essentially zero robustness margin. It would work perfectly for the exact system you modeled and catastrophically fail for any deviation from that model. This wasn't just a theoretical concern. There were real systems where optimal controllers, designed with great mathematical sophistication, performed terribly in practice because the models weren't accurate enough. The aerospace community, in particular, started to notice this in the late 1960s and 1970s. You'd have a linear quadratic regulator, that's the workhorse of optimal state feedback control, that looked perfect on paper but couldn't handle the real-world uncertainties. Now, to be fair, the LQR, linear quadratic regulator, actually does have some nice robustness properties when implemented as pure state feedback. There's a famous result showing that LQR controllers have at least 60 degrees of phase margin and infinite gain margin in each channel. That sounds great. But the catch is that in practice, you almost never have access to the full state. You have to estimate the state using an observer or a Kalman filter, and when you combine the optimal controller with the optimal estimator, a configuration sometimes called LQG for linear quadratic Gaussian, those beautiful robustness guarantees can evaporate completely. John Doyle at Caltech demonstrated this in a devastating 1978 paper with the memorable title, Guaranteed Margins for LQG Regulators, in which he showed that the guaranteed margins were essentially zero. There are no guaranteed margins. An LQG controller can have arbitrarily small stability margins. The paper was a wake-up call for the entire control community. Think about what that means for a moment. You've got this elegant mathematical framework, optimal control plus optimal estimation, and it produces controllers that are optimal in a very precise sense. They minimize your cost function. They're the best you can do, given your model and your noise assumptions. But optimality with respect to a model is not the same as good performance in the real world. The map is not the territory. And when the territory deviates from the map, your optimal controller might be worse than a simple, conservative classical design that a practicing engineer tuned by hand using Bode plots and intuition. This realization launched an entire new chapter in control theory, one that's sometimes called the robustness revolution. And it was driven by a fundamental question. Can we design controllers that are not just optimal for one specific model, but that perform well across a whole set of possible models? Can we explicitly account for model uncertainty in the design process? The answer turned out to be yes, but getting there required some of the most sophisticated mathematics that control theory has ever produced. The key figures in this story are John Doyle, who we just mentioned, George Zames at McGill University in Montreal, and a growing community of researchers in the late 70s and 80s who developed what's called robust control theory, and specifically a framework known as H-infinity control. Zames published a foundational paper in 1981 that reframed the control design problem not as minimizing the expected response to random noise, which is what LQG does, but as minimizing the worst-case response across all possible disturbances of bounded energy. It's a minimax philosophy. You're not optimizing for the average case. You're guarding against the worst case. And the mathematical tool for measuring this worst-case amplification is the H-infinity norm of the transfer function, which is essentially the peak of the frequency response magnitude. Now, this might sound like we've come full circle, and in a sense we have. Zames and the robust control community brought frequency domain thinking back into modern control. After 2 decades of state-space methods dominating the theoretical landscape, suddenly, transfer functions and frequency responses were relevant again, but now enriched with the state-space machinery and optimization tools that modern control had developed. It was a synthesis, a merging of classical intuition about robustness with modern mathematical power. And the person who did perhaps the most to bridge these worlds was Doyle, who along with Keith Glover and Bruce Francis developed computational methods for H-infinity controller design in the mid-1980s that made the theory actually usable by practicing engineers. But I want to slow down here and talk about what robust control really feels like, intuitively, because the mathematics can obscure something fundamentally simple and beautiful about the idea. Imagine you're designing a cruise control system for a car. Your model says the car weighs 1,500 kilograms, but in reality, sometimes the car is carrying just the driver, and sometimes it's fully loaded with passengers and luggage, and the weight might range from 1,300 to 2,000 kilograms. A non-robust design optimizes for exactly 1,500 kilograms and might perform poorly at the extremes. A robust design says, I need a controller that works acceptably well for any weight in that range. It might not be the absolute best at any single weight, but it's good enough across all of them. You're trading peak performance for consistency. And in most real engineering applications, consistency is exactly what you want. You don't want a car that drives beautifully when it's empty and terribly when it's full. You want one that drives well enough, always. This trade-off between performance and robustness is one of the deepest themes in all of control engineering, and honestly, it shows up everywhere in life. But in control theory, it became mathematically precise in the 1980s, and that precision opened up new possibilities for designing systems that worked reliably in the messy, uncertain real world. And the timing was perfect, because the systems that engineers were being asked to control were getting more and more complex, more and more safety critical, and the consequences of failure were getting higher and higher. Think about the systems that were emerging in the 1980s and 90s. Fly-by-wire aircraft, where there's no mechanical linkage between the pilot's stick and the control surfaces, just wires carrying electrical signals to actuators, with computers in between making thousands of adjustments per second. Nuclear power plants, where a mistake in the control logic doesn't just mean a product recall, it means potential catastrophe. Chemical processing facilities handling volatile, toxic substances at extreme temperatures and pressures. The electrical grid, growing, ever more interconnected, where a disturbance in one region can cascade across an entire continent in seconds. These aren't systems where you get to say, well, the controller works great most of the time. Most of the time isn't good enough when the stakes are that high. And here's the thing. These systems didn't just demand robustness. They demanded something else. Something that classical and even modern control theory hadn't fully grappled with yet. They demanded the ability to handle multiple interacting variables simultaneously. Let's talk about that, because it's one of those ideas that sounds obvious once you hear it, but actually required a fundamental shift in how engineers thought about control. Go back to the thermostat on your wall for a second. That's a single input, single output system. One input, the heater, and one output, the temperature. You measure the temperature. You compare it to the set point. You adjust the heater. Simple, elegant, and the kind of system that classical control theory handles beautifully. PID controllers, Bode plots, Nyquist diagrams, all of those tools were built for exactly this kind of problem. One knob to turn, one thing to measure. But now think about an airplane. You've got ailerons controlling roll, elevators controlling pitch, rudder controlling yaw, throttle controlling speed, flaps changing the lift characteristics, and every single one of these things affects every other one. When you deflect the ailerons to roll the aircraft, that doesn't just change the roll. It also creates what's called adverse yaw, where the nose swings in the opposite direction from the turn. So now, the rudder has to compensate. But the rudder deflection changes the side slip angle, which affects the lift distribution, which affects the roll you were trying to control in the first place. Everything is coupled. Everything talks to everything else. You can't just design 5 separate single-loop controllers and bolt them together, because they'll fight each other. They'll each try to correct for disturbances that the other controllers are actually creating. This is what engineers call a multivariable control problem, or MIMO. Multiple inputs, multiple outputs, and while the state space methods that Kalman introduced were theoretically capable of handling MIMO systems, the practical tools for designing robust multivariable controllers took decades to mature. The H-infinity framework was inherently multivariable, which was one of its great strengths, but there were other approaches too. And the story of how engineers learned to tame these coupled, interacting systems is really the story of control engineering growing up. One of the most dramatic examples of what happens when you get multivariable control wrong, or more precisely, when you don't fully account for the coupling between variables, is the story of the first fly-by-wire aircraft. Now, fly-by-wire had been experimented with since the 1950s and 60s, with modified military aircraft serving as test beds. But the first production fly-by-wire fighter jet was the General Dynamics F-16 Fighting Falcon, which flew in 1974 and entered service in 1978. The F-16 was deliberately designed to be aerodynamically unstable. Let that sink in for a moment. The engineers intentionally made an airplane that, without its computer, could not fly. A stable airplane, if you let go of the stick, tends to return to level flight on its own. The F-16 doesn't do that. Left to its own devices, it would pitch up and tumble out of control in less than a second. Half a second, actually, in some flight conditions. Why on earth would you design an airplane like that? Because instability buys you agility. A stable airplane resists changes in attitude. That's what stability means. But a fighter jet needs to change attitude rapidly, to pull hard turns, to snap from one maneuver to another. By making the airframe unstable, the designers gave the pilot, or rather, gave the flight control computer, the ability to command incredibly rapid maneuvers. The computer stabilizes the aircraft hundreds of times per second, making tiny adjustments to the control surfaces that the pilot never feels. From the pilot's perspective, the airplane handles beautifully. It goes exactly where you point it, instantly and precisely. But underneath that smooth experience, there's a control system working furiously, a multivariable controller managing pitch, roll, yaw, and their countless interactions, keeping an inherently uncontrollable machine perfectly controlled. And here's where it gets really interesting from a control theory perspective. The F-16's flight control system couldn't just be robust in the H-infinity sense of handling model uncertainty. It also had to handle gain scheduling, which is a concept worth spending a moment on because it shows up everywhere in modern control. The aerodynamic behavior of an airplane changes dramatically depending on speed, altitude, angle of attack, and configuration. The relationship between a control surface deflection and the resulting force on the aircraft is completely different at Mach 0.3 at sea level versus Mach 1.5 at 40,000 feet. The air is denser at low altitude, so the same control deflection produces much more force. The dynamics change, the coupling between axes changes. It's almost like you're controlling a different airplane at different points in the flight envelope. So what do? You design multiple controllers, each optimized for a specific flight condition, and you smoothly switch between them, or blend them, as the conditions change. That's gain scheduling. You measure the current speed, altitude, angle of attack, and you use those measurements to look up or interpolate the appropriate controller gains. It's an elegant, practical solution, and it works remarkably well, but it also introduces its own challenges. What happens during the transitions between different controller settings? Can you guarantee stability during the blend? These questions drove a whole branch of control research in the 80s and 90s. The Airbus A320, which entered service in 1988, brought fly-by-wire to commercial aviation, and that raised the stakes enormously. A military test pilot accepts a certain level of risk. 300 passengers on a transatlantic flight do not. The A320's flight control system had to be not just robust and multivariable and gain-scheduled, but also fault-tolerant. It needed redundancy. Multiple computers running different software, designed by different teams, so that a single software bug couldn't bring down all the channels simultaneously. This idea of dissimilar redundancy is fascinating. You don't just have 3 copies of the same computer. You have 3 computers designed by different teams using different programming languages and different hardware, all solving the same control problem. The theory is that they're unlikely to all fail in the same way at the same time. If one gives a wrong answer, the other 2 outvote it. But even with all that redundancy, there were incidents. In June 1988, an A320 performing a low-altitude flyover at an air show in Hobsheim, France, crashed into trees at the end of the runway. The investigation was controversial and remains debated, but it raised questions about the interaction between the flight control laws and the pilot's expectations, about what happens when the computer and the human disagree about what the airplane should be doing. The flight control system had protections built in to prevent the pilot from exceeding safe flight parameters, like angle of attack limits. But in that low-altitude, low-speed situation, those protections may have prevented the pilot from commanding the climb rate needed to clear the trees. The human thought one thing should happen. The computer enforced something else, and the result was a tragedy. This tension between automation and human authority became one of the defining questions of control engineering in the late 20th century. It's not a purely technical question. It's deeply human. How much authority do you give the machine? If the computer knows the aerodynamic limits better than the pilot, should it always have the final say? But what if the computer's model is wrong? What if the sensors feeding it data are giving bad information? The pilot can look out the window. The pilot has judgment, intuition, the ability to handle situations that no programmer ever anticipated. So who should be in charge? Boeing took a different philosophical approach with the 777, which entered service in 1995. It was also fly-by-wire, but Boeing's design philosophy preserved more pilot authority. The control system would push back against dangerous commands. The pilot would feel resistance in the stick, but it wouldn't absolutely prevent the pilot from overriding the protections. The idea was that in an unforeseen emergency, the pilot might need to exceed normal limits to save the aircraft. Airbus's philosophy was more protective. The computer enforces hard limits because, statistically, more accidents are caused by pilots exceeding limits than by pilots needing to exceed them. Both philosophies have their logic. Both have their risks. And the debate between them is still not fully resolved. Now, I want to pull back from aviation for a moment, because this same question, how do you design control systems that work with humans rather than against them, shows up in every domain where automation is advancing. Think about your car. Modern vehicles have electronic stability control, which detects when you're starting to skid and selectively applies brakes to individual wheels to keep you on your intended path. It's a control system that intervenes without asking permission, and it saves thousands of lives every year. Studies in the early 2000s estimated that electronic stability control reduced single-vehicle crashes by about 35% and single-vehicle fatal crashes by about 30%. That's an extraordinary number, and yet, when these systems were first introduced, there was resistance. Drivers didn't like the feeling of the car doing something they didn't command. Racing drivers especially complained that the system interfered with techniques like controlled drifting. The resolution, in most cases, was to make the intervention invisible. The best stability control systems act so quickly and so subtly that you never even realize they've activated. You just feel like you're a better driver than you actually are. And that's a profound insight about control system design. The best controller is one you never notice. It does its work quietly, in the background, making the system behave the way you expect it to, smoothing out the disturbances and uncertainties before you ever become aware of them. This idea connects back to something we touched on much earlier, the way Watt's governor worked silently on the steam engine, maintaining speed without anyone having to think about it. The principle hasn't changed in 250 years. What's changed is the complexity of the systems, the sophistication of the mathematics, and the speed of the computers executing the control laws. But the fundamental goal: make the system do what it's supposed to do, reliably, in the face of uncertainty and disturbance. That's been the same since the beginning. And as we moved into the 1990s and 2000s, a new kind of control problem started demanding attention, one that pushed the boundaries of everything we've talked about so far. These were systems where the controller didn't just have to react to what was happening right now. It had to look ahead, to anticipate what was coming, and to plan its actions over a future time horizon while respecting constraints. Engineers call this model predictive control, and its story begins, of all places, in the petroleum refineries of the Gulf Coast in the 1970s and 80s. Places like Houston, Baton Rouge, refineries stretching along the ship channel, where crude oil comes in one end and dozens of different products come out the other. Gasoline, diesel, jet fuel, lubricants, petrochemical feedstocks. And the thing about a refinery is that it's not one process, it's hundreds of interconnected processes, all running simultaneously, all affecting each other. You change the temperature in one distillation column, and it shifts the composition in 3 downstream units. You adjust a flow rate here, and the pressure changes over there. It's a massively coupled system, exactly the kind of multivariable problem we were just talking about with fly-by-wire aircraft, except in some ways it's even harder because the dynamics are slower, the interactions are more complex, and the economic stakes of running inefficiently are enormous. We're talking about facilities processing hundreds of thousands of barrels of crude per day. Even a 1% improvement in efficiency can mean millions of dollars a year. Now, refineries had been using PID controllers for decades by this point, thousands of them, each one managing a single loop, a temperature here, a pressure there, a level somewhere else. And they worked, mostly. But here's the problem. Each of those PID controllers was doing its own thing independently, reacting to its own measurement, adjusting its own valve. None of them knew what the others were doing. And in a tightly coupled system, that's a recipe for fighting. One controller opens a valve to raise temperature, which increases pressure somewhere else, which causes another controller to close a different valve, which drops the flow rate, which makes the first controller work even harder. They end up wrestling with each other, and the whole system oscillates or settles into some compromise that's stable but far from optimal. What the refinery engineers wanted was something smarter. They wanted a controller that could look at the whole picture, all the variables, all the interactions, and figure out the best set of moves simultaneously. And here's the crucial part. They needed it to respect constraints. Real physical constraints. You can't heat that column above a certain temperature, or the catalyst degrades. You can't exceed a certain pressure, or the safety valves blow. You can't change the feed rate faster than a certain amount, or you'll upset the downstream units. And you have product specifications to meet. The sulfur content in the diesel has to be below a certain threshold. The octane number in the gasoline has to be above a certain level. These aren't suggestions. These are hard limits. Traditional control theory, even the beautiful state space methods of Kalman, didn't handle constraints very naturally. You could design an optimal controller using LQR, and it would give you this elegant feedback law, but it assumed the actuators could do whatever the math told them to do. In reality, every valve has a maximum and minimum opening. Every heater has a maximum duty. When you hit those limits, the elegant math breaks down. Engineers had workarounds, anti-wind-up schemes, for instance, to keep integral action from accumulating when an actuator saturates. But these were patches, not solutions. Model Predictive Control, or MPC, took a completely different approach. And the idea, when you hear it, is almost obvious in retrospect, which is usually a sign that it's genuinely deep. Here's how it works. You build a mathematical model of your process, a model that captures how the outputs respond to changes in the inputs over time. At every control step, you use that model to predict what the process is going to do over some future time window. Maybe 30 steps ahead, maybe 60, depending on the application. Then you set up an optimization problem. Find the sequence of control moves over that future window that minimizes some cost function. Maybe the deviation from your desired set points, maybe energy consumption, maybe both, while satisfying all the constraints. Every constraint. The valve limits, the temperature limits, the pressure limits, the product specs, all of them. You solve that optimization problem. You get a whole sequence of future control moves, but you only apply the first one. Then you measure what actually happened, you shift the window forward by one step, and you solve the whole optimization problem again with the updated measurements. This is called the receding horizon, and it's what makes MPC so powerful and so robust. You're constantly replanning, constantly correcting, constantly incorporating new information. Think about it like driving a car on a winding mountain road. You don't just look at the road right in front of your bumper and react. You look ahead, you see the curve coming, and you start adjusting your speed and your steering before you reach it. And if something unexpected happens, a rock in the road, a gust of wind, you replan on the fly. That's what MPC does. It's anticipatory. It plans ahead while respecting the physical limits of the system. The earliest industrial MPC algorithms appeared in the late 1970s. Two are usually credited as the pioneers. One was called Dynamic Matrix Control, or DMC, developed by Charlie Cutler and Brian Ramaker at Shell Oil. They published their key paper around 1980, though the work had been going on internally at Shell for a few years before that. The other was called Model Algorithmic Control, developed by Jacques Richelet and colleagues in France, published in 1978. Both approaches used step response or impulse response models. Basically, you'd bump an input and record how each output responded over time, and that collection of response curves became your model. Simple, practical, easy to identify from plant data. No need for the kind of first principles physics models that academic control theorists preferred. This was engineering pragmatism at its finest, and it worked. It worked remarkably well. Refineries that implemented DMC saw immediate improvements: tighter control, less variability, the ability to push operating points closer to constraint boundaries where the economics were better. If your product spec says sulfur must be below 50 parts per million, and your old PID-based system had so much variability that you had to target 30 just to make sure you never exceeded 50, well, MPC could tighten that variability so you could target 45 and still never violate the constraint. That difference, running closer to the limit, translated directly into higher throughput, lower energy consumption, better product yields. The payback periods on these MPC installations were often measured in months, sometimes weeks. Now here's what's interesting from a theoretical standpoint. The academic control community was initially somewhat dismissive of MPC. It didn't fit neatly into the elegant frameworks they'd been building. It was computationally expensive. You had to solve an optimization problem at every single time step. In the 1970s and 80s, that meant serious computing hardware, and it limited MPC to slow processes where you had seconds or minutes between control actions, which is why refineries were the perfect first application. The dynamics of a distillation column play out over minutes to hours. You had time to solve the optimization. But the academics also had legitimate concerns. Where were the stability guarantees? Classical and modern control theory could prove mathematically that a closed-loop system would be stable. Early MPC didn't have those proofs. It worked in practice, but could you prove it would always work? What if the model was wrong? What happened at the edges of the constraint set? These were real questions, and they drove a productive collision between industrial practice and academic theory throughout the 1980s and 90s. Researchers like David Main, James Rawlings, Eduardo Sontag, and many others worked on establishing rigorous stability theory for MPC. They showed that if you added certain terminal conditions to the optimization, a terminal cost, a terminal constraint set, you could guarantee stability. The theory caught up with the practice, and MPC became one of those rare areas where industry was ahead of academia for a while, and then the two met in the middle and made each other better. And then something happened that changed MPC's reach entirely. Computers got fast, really fast. By the 2000s, processors were powerful enough to solve the optimization problems that MPC required not in seconds, but in milliseconds. And that opened the door to fast systems, systems with dynamics that played out not over minutes, but over fractions of a second. Systems like, well, cars, and power electronics, and robots. And eventually, the thing that brought MPC into the spotlight more than almost anything else, autonomous vehicles. Think about what a self-driving car has to do. It needs to follow a planned path, maintain a safe speed, stay in its lane, avoid obstacles, obey traffic rules, and do all of this while respecting the physical limits of the vehicle: maximum steering angle, maximum braking force, tire grip limits that change with road conditions. It needs to look ahead, to anticipate curves and stops and lane changes. It needs to handle uncertainty, other drivers doing unpredictable things, pedestrians stepping off curbs, construction zones that weren't on the map. This is an MPC problem through and through. You have a model of the vehicle dynamics, you have a prediction horizon, you have constraints, and you have a cost function that balances path following against comfort, against safety. Many of the motion planning and control stacks in autonomous vehicles today use some form of model predictive control at their core. But MPC's modern reach goes far beyond cars. It's in building climate control systems, where the controller predicts the thermal behavior of the building over the next few hours, accounts for weather forecasts and occupancy schedules, and optimizes heating and cooling to minimize energy cost while keeping everyone comfortable. It's in wind turbines, where the controller looks at incoming wind measurements and adjusts blade pitch and generator torque to maximize energy capture while keeping structural loads within safe limits. It's in the power grid itself, where system operators use MPC-like approaches to schedule generation and manage transmission constraints across entire regions. And here's something beautiful about how this connects to the larger story we've been telling. Remember Kalman's state estimator, the filter we talked about earlier, the one that Stanley Schmidt flew on Apollo? In many modern MPC implementations, a Kalman filter sits right at the front end, estimating the current state of the system from noisy measurements, and then feeding that estimate into the MPC optimizer, which plans the future trajectory. Kalman and MPC working together, the observer and the controller, estimation and optimization, two halves of the same coin. Kalman himself might have appreciated the elegance of that pairing, the way his 1960 filter found its natural partner in an optimization framework that didn't fully mature until decades later. And there's another thread worth pulling on here, because as control systems grew more sophisticated, as they moved from single PID loops to multivariable state space designs to model predictive controllers running on powerful computers, something else was happening in parallel, something that would eventually intersect with control theory in ways that nobody quite expected. Machine learning was waking up. Neural networks, which had been around in various forms since the 1940s, were having their own renaissance. And people started asking a natural question. If you can learn a model of a system from data, if you can learn a control policy directly from experience without ever writing down the equations of motion, does that change everything we've been talking about? Does it make all of this classical and modern control theory obsolete? Or does it need control theory more than ever? That question, the collision and collaboration between learning and control, is one of the most fascinating conversations happening in engineering right now, and it tells you something profound about where control systems are headed. And maybe, just maybe, about where they've always been going. So let's think about this carefully. Because the hype around machine learning and artificial intelligence can make it sound like everything that came before is suddenly irrelevant, like all those decades of Bode plots and Nyquist criteria and Kalman filters and Riccati equations were just placeholders until the real technology showed up. And that's not only wrong, it's dangerously wrong in a way that the history we've been walking through tonight actually helps explain. Here's the thing about neural networks and control. The basic idea is seductive. You have a system, a robot arm, a chemical reactor, a self-driving car, and instead of carefully deriving a mathematical model of that system, instead of identifying all the parameters and linearizing around operating points and designing a controller based on that model, you just let a learning algorithm figure it out. You give it data, lots and lots of data, inputs and outputs, states and actions, rewards and penalties. And the neural network learns, through millions of iterations, what to do. It learns a policy, a mapping from what the system is doing right now to what the controller should command. No equations of motion required, no transfer functions, no state space matrices, just data and computation. And honestly, it works. Sometimes it works astonishingly well. DeepMind's work on controlling plasma in a tokamak fusion reactor, published around 2022, used deep reinforcement learning to shape and stabilize the superheated plasma inside the TCV tokamak in Switzerland. The plasma in a fusion reactor is one of the most complex, non-linear, fast-moving systems you can imagine. It's a roiling mass of charged particles at 100 million degrees, held in place by magnetic fields, and it wants nothing more than to touch the walls and snuff itself out. Traditional control approaches work, but they struggle with the full complexity. The DeepMind team trained a neural network controller in simulation and then deployed it on the real reactor, and it managed to hold the plasma in configurations that would have been extremely difficult to achieve with conventional methods. That's genuinely impressive. Or think about the robotic manipulation work coming out of labs at Berkeley and Stanford and various companies. Robots learning to pick up objects they've never seen before, to fold laundry, to insert pegs into holes with sub-millimeter precision. Tasks that would be nightmarishly complex to program explicitly because the contact dynamics are so hard to model. Learning from experience, from trial and error in simulation, and then transferring to the real world. There's real magic there. But here's where the story gets more nuanced, and where all those decades of control theory we've been talking about start reasserting themselves. Because there's a difference between a demonstration that works in a lab and a system you'd trust your life to. And that difference is exactly the territory that control theory has been mapping for over a century. Think back to what happened with LQG. Remember that? Kalman's beautiful optimal control framework, mathematically elegant, minimizing a cost function, producing the best possible controller. And then Doyle comes along in 1978 and shows that it has, essentially, zero guaranteed robustness margins. It could fall apart with the tiniest perturbation. The math said it was optimal, but optimal with respect to a specific model, and the real world is never exactly your model. That lesson, that gap between theoretical optimality and real-world robustness, is arguably the central lesson of control engineering, and it applies to learned controllers with even more force. When a neural network learns a control policy from data, what has it actually learned? It's learned a mapping that works well on the data it was trained on in the scenarios it experienced during training. But what about scenarios it hasn't seen? What about the edge cases, the rare disturbances, the sensor failures, the conditions that sit just outside the training distribution? A neural network, unlike a carefully designed, robust controller, gives you very few guarantees about what it will do in those situations. It might do something reasonable. It might do something catastrophic. And crucially, you often can't tell in advance which one it will be, because the internal workings of a deep neural network are notoriously difficult to interpret. Now you might be thinking, well, just train it on more data, cover more scenarios. And that helps. It genuinely does. But here's the fundamental problem. For safety-critical systems, you don't just need a controller that usually works. You need one that always works, within defined bounds, under specified conditions. You need guarantees, and guarantees are precisely what classical and modern control theory were designed to provide. Stability proofs, robustness margins, worst-case performance bounds, the entire apparatus of Lyapunov theory, of H-infinity design, of robust control. That's all about providing mathematical certificates that the system will behave within acceptable limits no matter what happens, as long as the uncertainty stays within a characterized set. So what's actually happening in the most thoughtful and productive corners of the field is not a replacement of control theory by machine learning. It's a merger, a collaboration, and it's happening in several really interesting ways. One approach is to use machine learning to build better models and then use those models inside conventional control frameworks, Remember how MPC needs a model of the system to predict future behavior? Well, what if that model is partially or entirely learned from data? You might have a physics-based model that captures the broad strokes, the basic dynamics, the conservation laws, the known relationships, and then use a neural network to learn the residual, the part that your physics model gets wrong. The unmodeled dynamics, the friction effects, the aerodynamic interactions that are too complex to derive from first principles. This is sometimes called gray box modeling or physics-informed learning, and it gives you the best of both worlds, the interpretability and extrapolation ability of physics-based models, plus the flexibility and accuracy of learned components. And then you wrap that hybrid model inside an MPC framework that respects constraints and provides some level of guaranteed performance. The learning makes the model better. The control theory makes the system safe. Another approach goes the other direction. You let the neural network learn a control policy, but then you verify it using tools from control theory. Can you prove that this learned controller stabilizes the system? Can you find a Lyapunov function? Remember, that's a mathematical energy-like quantity that decreases over time, proving stability for the closed-loop system with the neural network in the loop. This is an active area of research, and it's hard because neural networks are complicated nonlinear functions with millions of parameters. But people are making progress. Researchers like those in the groups of Russ to Drake at MIT and Marco Pavone at Stanford have been developing methods to either verify learned controllers after the fact or to bake stability guarantees into the learning process itself, constraining the neural network during training so that the resulting controller is guaranteed to be stable. And then there's reinforcement learning with constraints, where the learning algorithm itself is designed to respect safety constraints during both training and deployment. Instead of just maximizing a reward signal, which is how basic reinforcement learning works, and which can lead to all sorts of dangerous behaviors as the agent finds creative ways to game the reward, you add hard constraints that the agent must never violate. Keep the aircraft within its flight envelope. Never exceed the structural load limits. Stay within the lane. This connects directly to the constrained optimization at the heart of MPC, and some of the most promising recent work essentially combines reinforcement learning with model predictive control, using learning to improve the model or the cost function while using MPC's constraint handling machinery to keep things safe. There's a beautiful irony here if you step back and look at the big picture. The field of control theory spent decades developing rigorous mathematical tools for analyzing and designing feedback systems. Then machine learning came along and said, we don't need all that math. We have data. And now, as machine learning tries to move into safety-critical applications, autonomous vehicles, surgical robots, power grid management, aerospace, it's discovering that it needs exactly that math. It needs stability theory. It needs robustness analysis. It needs the tools that Lyapunov and Nyquist and Bode and Kalman and Zames and Doyle developed. The data-driven approach and the model-based approach aren't rivals. They're complementary, and the most powerful systems of the future will almost certainly use both. Think about a self-driving car for a moment, because it brings together almost everything we've talked about tonight. There are Kalman filters, or their nonlinear cousins, extended and unscented Kalman filters, fusing data from cameras, LiDAR, radar, GPS, and inertial sensors to estimate where the car is and what's around it. That's estimation, straight from Kalman's 1960 paper, the same math that guided Apollo. There's model predictive control planning the car's trajectory, looking ahead a few seconds, optimizing a path that follows the road, avoids obstacles, respects speed limits and acceleration comfort bounds, all while handling constraints on steering angle and braking force. That's the MPC we just talked about, descended from those Gulf Coast refinery controllers. There are neural networks doing perception, recognizing pedestrians, reading traffic signs, understanding the scene. That's machine learning at its best, doing things that would be nearly impossible with hand-coded rules. And there are stability and safety systems underneath everything, ensuring that the car's behavior stays within safe bounds no matter what the higher-level algorithms decide. That's classical, robust control, the legacy of Zames and Doyle and the entire H-infinity revolution. Every layer of that system represents a different era in the story we've been telling. The float valve in Ctesibios's water clock, Watt's governor, Maxwell's differential equations, Black's feedback amplifier, the Sperry gyroscope, the Apollo guidance computer, the Shell refinery optimizer. They're all there, layered on top of each other, each generation building on the one before. And you know what's remarkable? Even with all of this sophistication, all these layers of estimation and prediction and optimization and learning, the fundamental idea hasn't changed. It's still feedback. It's still measure what's happening, compare it to what you want, and adjust. That's what Ctesibios's float valve did 2,000 years ago. That's what a thermostat on your wall does. That's what a billion-dollar autonomous vehicle platform does. The principle is the same. The math has gotten more powerful, the systems more complex, the applications more ambitious. But the core insight, that you can use information about the current state of the world to make better decisions about what to do next, that insight is timeless. And maybe that's the most comforting thing about all of this, as you're lying here, letting these ideas wash over you. The world is full of systems that are quietly, invisibly keeping things stable. The temperature in this room, the voltage in the power grid feeding the device you're listening to, the pressure in the water pipes, the flight path of every airplane overhead, the idle speed of every car engine on the street outside, all of them held steady by feedback loops that someone, somewhere designed, drawing on ideas that stretch back through Doyle and Zames and Kalman and Bode and Nyquist and Black and Minorski and Maxwell and Watt, all the way back to a Greek inventor in Alexandria who just wanted his water clock to keep better time. These systems don't demand your attention. They don't announce themselves. They just work, quietly, in the background, keeping the world from drifting too far from where it should be. And there's something deeply reassuring about that, about knowing that even in a world that can feel chaotic and unpredictable, there are these elegant mathematical structures, these carefully designed loops of measurement and correction, holding things together. Feedback is everywhere, and it's working right now, all around you, as steady and patient as gravity. So let that thought settle. Let the details blur if they want to. The names and dates and equations, they'll be there if you ever want to come back to them. What matters, what you can carry with you into sleep, is the shape of the story. People noticed that systems drift. They invented ways to measure the drift and push back against it. They figured out the math to do it well, and then better, and then optimally, and then robustly. They argued and failed and tried again, and the systems they built are all around you now, invisible and faithful, doing exactly what they were designed to do. The world is a little more stable than it would be without them, and right now, that's a nice thing to know.